Thank you. So yeah, I'm going to be talking about how do we sort of scale geophysical monitoring. And so for those of you that are already into the weeds on geophysical methods, this will stay a little high level, but hopefully for those of you that are more on the policy and government side, you'll get some points where you're able to connect with sort of what's going on in this project, because geophysical monitoring is awesome. It lets us see below the surface of the earth in a way that is beyond what remote sensing techniques are able to do. But it can be really expensive to do. So a lot of times it's not applied at large scale unless there's a lot of money involved as far as profits for maybe oil and gas companies, mining projects, that sort of thing. So we're looking at how do we kind of make this so that it's affordable and can be applied throughout permafrost regions. So we're going to look first at just a basic intro to geophysics if you haven't been exposed to it before, so we're all kind of on the same page. How does seismic imaging and other types of geophysical imaging connect to properties of our permafrost? We're going to look at a specific use. And then we're going to look at how do we actually scale this up. So if you're not familiar with geophysical imaging, it's a lot like medical imaging. Most of us know about things like ultrasound imaging, where mechanical vibrations are to the body. Those vibrations bounce back from the source and then are detected by sensors. And we infer what are those materials within the body. We map that out in 2D or even 3D. And we have a lot of different types of medical imaging. We also have a lot of types of medical imaging based on electrical or electromagnetic as well.
Why'd she do that?
So the sensors measure these waves, whether it's mechanical or electromagnetic, and then we infer how fast did those waves move in different spots. And so when we do this with geophysics, it's a lot like what you see on the right. We've got a bunch of different sensors, and then we've got a source, which in our case is just a simple hammer attached to a GPS timer that tells us when did we hit that. And then our sensors also are attached to GPS timers, so they can say, how long did it take to get to each one of those? And then we can start to say, on this little section of our sensor array, was it moving faster or slower? If it moves slower, that means that the permafrost might be weaker there. It might be thawed. If it moves faster, you probably have a lot more ice content. It's a lot more structurally sound. And there's a lot of different characteristics of your soil type, whether it's wetter or drier, how much is the ice content, what's the type of soil. All of that actually governs what those speeds of propagation are for our seismic waves. I'm not going to bother walking you through this chart on the right because there's many different variables going on, but we've got a pretty good handle on this. So Xiaoheng Ji, who's a student of Ming's, has done a great analysis of all the many different models of permafrost properties connecting to seismic velocities so that we can really pin down when we measure seismic velocities of different types, what does that tell us about how strong our soils are? Okay, so we decided we want to do some geophysical imaging, and we needed to have a test site where we were interested in looking at both areas where there's some disturbed permafrost close to infrastructure, as well as some undisturbed permafrost. It's more just out on the tundra, the natural conditions that you might expect.
Now everybody can see you.
So we're close to Dewline Road, which is actually just to the east of where Nanook's Den is, where we all stayed. There's a Navy facility there. There's a DOE facility, and there's a NOAA facility. So a lot of infrastructure that we could build on for our research project. So over here on the top right, you see our study region area. And if we zoom in, we can see that there's sort of a road there, as well as a few different spots around the NOAA building. And then we had a bunch of sensors that went off into the tundra, whether it was seismic sensing, electromagnetic sensing, like what we call ERTs, or temperature boreholes there as well. We were able to capture a variety of different conditions here. As we got close to the buildings, we had sort of our road that you can see down here. It was a little bit drier, but also some ponds, thermokarst that had evolved there, like we've seen on our trip so far. As we got further into the tundra, around here, like MSW2 area is what we call that. There, it's a lot drier, but then we got into an area that was much more like ponds and low-centered polygons, much wetter conditions there. And we wanted to be able to try out this installation that we did in so many different areas. Okay, so we did these seismic imaging experiments. We hit our hammer a ton of times on an array. And just to get a first feel for what our profiles look like in depth, we were able to get seismic velocity profiles at many different locations. So we've got 4 different locations that we're just going to call sites 1 through 4 out in the tundra where it's relatively undisturbed. And I say relatively undisturbed, there's actually quite a bit of hunting and other activities, recreation out in this area. And so there are some areas like ASW1 where we see a lower seismic velocity, indicating kind of weaker permafrost there. We've got thicker active layers as well in that area. And we did notice that there were a lot of like tire tracks and things like that for trails in that area compared to some of the other locations where we had sort of higher velocities, meaning stronger permafrost. As we got way out into the lakes area, which we call MASW4 here, we did start to see velocities go down again. We have a lot of thermokarst there. It's not surprising that as you have those lakes going on, you do get seismic velocities that are lower in those areas. But as we started doing seismic imaging down in this area along the roadside and close to the buildings, we saw much lower seismic velocities overall. And not just lower velocities, but also thicker active layers. That means deeper thaw depths. And we also noticed that as we were closer to building areas, we saw a more pronounced effect than as we got farther away from those areas. At each one of these spots, we didn't just do a 1D profile where we said at every depth, what's our seismic velocity? We actually did 2-dimensional imaging, and I'll just show you one of those so you get a feel for what that looks like. So this stuff that we considered it undisturbed permafrost. And so we had a little 24-meter region. And across that 24 meters, you can see here, you go through different depths, just down to about 8 meters or so, and different locations in space. And then at every location, we've got a pixel colored that says, what's our seismic velocity there? And we see this huge amount of variation. When we just did our 1-dimensional image where we said, what's our profile here at every depth? We got this and it seemed pretty reliable. We had sort of a good fit to our data. But as we started to do our more advanced 2-dimensional imaging, we see a lot more details there. And we see a lot of heterogeneity laterally, which corresponds to the same thing that we see on our surface conditions as well. So we're really seeing that where we have remote sensing able to do sort of fine scale variations that it can pick up over these large distances, our geophysical imaging has the capability to detect that kind of scale of fine scale variations like we see in permafrost as well, but underneath the surface, seeing much deeper than skin depth, right? So just to make sure we're all on the same page of what we're looking at in this image, we've got sort of lower ice content off on the southwest region, closer to 0 to 5 meters, and more ice-rich permafrost up in the northeastern region of that little transect. Okay, so we're seeing that we can maybe see a lot more details if we're starting to do 2-dimensional imaging, if we've got many locations. But this also tells us that if we're just looking at a few locations with our geophysics, we're probably missing a lot of details. Even across this 2-kilometer region where we actually did our study, we see a huge variation in our conditions. And as we've been flying around, we've certainly all noticed that we have that kind of issue. So these 1D profiles are not really capturing that. There is still a little bit of uncertainty when we're just using seismic imaging to be able to do that interpretation and really tie it to the geology of what's going on under the surface. And so we've also done at certain locations multiple types of geophysics to really build up our interpretations better. And so having a few sites where we actually do that kind of detailed analysis is really helpful for us. So we've got our seismic imaging over here on the left. And then for the same location, we've got electrical resistivity tomography. It's just another type of geophysical imaging that uses electromagnetics on the right. And we were able to interpret the same sort of features out of those and have more certainty in how we were interpreting what we were seeing. We also had a few shallow borehole or core samples that we took as well as temperature sensing there. So this all helps to build up a more complete interpretation for us. Okay, but we want to actually scale this up. It's a lot of effort to go out and set off these hammer sources to send your team in and out. You're trampling all over the tundra, maybe possibly destroying the thing that you're trying to study if you're trying to do this repeatedly while you're doing some multi-year monitoring study. And so we're trying to get something that really is sort of a leave it and forget it type of system. And for us, that's been distributed fiber optic sensing methods. So I've been working with these for about 9 years now in a variety of different contexts. And they tend to be really good for when you need to have a sensor that you're going to be able to leave in place for a long time. You want to be able to just not install it once, or you want to be able to just install it once and then not have to come back too often. You also might be interested in things like being able to do fine scale monitoring. So if I put in the type of USGS seismometer that's sitting out close to our study area, it's a huge amount of effort and it only tells us about one specific location. But with these fiber optic sensing cables, what we're able to do with those is break them up into little sections along the cable. So that basically every 1 to 2 meters of cable acts as a separate sensor. So we have thousands of sensors installed in our little 2-kilometer study area. So that allows us to have the kind of resolution that we need to really pinpoint where there might be issues starting before they start to show up as surface changes, which is all that would have been possible before with remote sensing techniques. Okay, this is what the system looks like. I know a few of you went over to the DOE ARM facility and might have seen my instruments in there. So we've got a distributed acoustic sensing system down here on the bottom. That's what lets us do seismic imaging. And then up on the top, we've got a distributed temperature sensing system. And in the same locations, it's measuring temperatures in the subsurface. These create a lot of data compared to what we've worked with historically. For seismic monitoring, it's something like about 1,000 to 100,000 times faster rates of data acquisition than what we've previously typically worked with for environmental seismology problems. And so we have done quite a bit of work on doing things like edge computing, taking advantage of new algorithms that we've created, working with compressed data, and all that good stuff. But that's a lot of math, and we've all been working very hard the last 2 weeks, so probably not up for a lot of math today. But one of the things that I think was really useful about this study was also kind of pinning down what is the right way to install these sensors, whether it's distributed temperature sensing, distributed acoustic sensing, strain sensing. We're also working on distributed electromagnetic sensing, not at this site, but on other projects. And how do we install those cables so that they're not going to cause issues like what we've seen with those big trenches that have been put out? I can't fix the big trenches. This is Lorraine's specialty, but at least for installing it in the first place, we want to make sure we're not destroying the thing that we're trying to study. We want to make sure that like the temperatures we measure are actually representative of the ground temperatures around and not just representative of very disturbed soils. So we installed these 2-kilometer long cables. We've got 2 of them, one for temperature, one for acoustics. And it turns out we were working in the NOAA clean air area where you can't use a lot of sort of combustion motors. That rules out a lot of machinery that otherwise has been developed for fiber optic telecommunications in recent years to make it less invasive. But we had some nice strategies of being able to bundle up our spools into small bundles and sub bundles, walking them out onto the terrain in these sort of trains that we would hike along, and then being able to sort of wedge in shovels, wedge aside that permafrost on that organic layer. And we would basically put in a little cable, just using a wrench, simple stuff. And we did this for 2 kilometers. So over on the far right, you can see a picture I took this past week. It's been in place for 2 years now. And if I take away that line, I don't know if anybody here would be able to distinguish our trail from just the rest of the ground. Put it back, maybe you can see it. If you get up close, sometimes it looks a little bit like a lemming trail. And a lot of times when we were trying to track it down, we've actually just followed lemming trails on accident and had to go back and find where we really were. So we're trying to keep it as minimally invasive as possible. We're starting, this photo was taken this week, so two years after the initial installation. And so we're gonna keep tracking it as long as we're able to keep the cable in place. We are starting to get a little bit of small vegetation that's growing into the crack itself this year, which we didn't see as much of last year. And so I'm really happy to start seeing that on a relatively short time scale without doing any kind of seeding efforts or things like that. All right. So just to take a quick look at what this data looks like, if we took our whole array of cable, it's mapped out over here on the right. We started our Department of Energy DOE building and go out from there into the tundra. It's a little hard to see when we look at the whole thing. The DOE building is pretty hot, and we're sensing that on some of our cable that's indoors. So let's zoom in a bit. And if we just look at, say, the near infrastructure temperatures, this is the cable that's going from a building out along a road. And then it's stapled underneath the NOAA building, so like right under the pilings and the structure of the building. Yeah, the date on this is July 27th at 11 a.m. local time, roughly. So 10:58 a.m. It was kind of a warm day that day. And so we can really see that like along the infrastructure, it does get quite warm. And especially there are some areas where it's on the roadside where we had to go up into the embankment just a little bit to avoid a pond. And it's particularly hot right there. But as soon as we start getting out onto the tundra, we see that temperature drop. But it's not really like quite as uniform as we had expected. We thought it would just be every polygon has a pretty uniform temperature within it, but we do see a fair amount of variation there. And so trying to understand that better and track down what we can about sort of surface expression. One of the things, though, you could take away from this is if you were to just choose a few points to do temperature sensing in a more traditional way with thermistors, you might accidentally miss this trend overall if you weren't really good at site selection. In addition to the temperatures, we also see a lot of seismic signals that we're learning how to use as far as we see vehicles going along the road that we've been able to use for imaging. We see ice cracking in the permafrost and are learning how to correlate that with the temperatures outside. We also see sea ice and just other ocean noise in general. So anyways, we've been able to see a lot of more detail than we've been able to see in the past. And we think that's really useful for being able to study these sort of large region but fine scale processes that permafrost has. So if you want to try out these methods, check out CTEMPS to get low cost instruments or DASCOR for being able to do the kind of software processing that we have to with these massive data sets. So thanks.